This is section 4.8b, Real-Life Applications of Trigonometry. Today we're going to talk about harmonic motion. And harmonic motion is something that we see in nature, and it's something that you've seen before. For example, if you've ever seen a pendulum, like one of those old grandfather clocks, a pendulum swings back and forth. That's an example of harmonic motion. Harmonic motion is any type of oscillating or going back and forth type of motion. A ball, bobbing up and down on a spring is harmonic motion. A buoy that bobs up and down on the ocean surface is an example of harmonic motion. A sprinkler that goes back and forth through the same portion of a lawn and keeps going back and forth through that same portion of the lawn, that's also an example of harmonic motion. Now, the interesting thing we're going to see in this section is how harmonic motion relates to sine and cosine waves. But let's just study this example to make sure we understand it. This is a classic example of harmonic motion, which is a ball that is bobbing up and down on a spring. Now, if you take apart a ballpoint pen, for example, the kind that you can click in and out, they have springs, and if you look at that spring, you can see that the spring can be both compressed and stretched. But if you're not trying to compress it and you're not trying to stretch it, it has a resting length. That would be called the equilibrium point, when the spring is neither stretched nor compressed. All right, let's look at this example here. We have time being represented on the x-axis, and the distance from the equilibrium point is represented by the y-coordinate on the y-axis. Let's look at this top graph first. By the way, this top graph and this bottom graph are just they're two different graphs for the same reality. It's just that it's a little less cluttered to do it this way. Okay, so let's look at the top graph first. Look at where the mouse arrow is circling now. It's just outlining this red ball. And the red ball at this starting moment is at equilibrium position because the spring is neither stretched nor compressed. Okay, so think of these gray drawings as cartoon drawings. You know, if you read a cartoon or look at a comic book, they simulate animation just by showing that in successive frames there could be a difference in position, and that simulates motion. Alright, so we just have one spring here, not a bunch of different ones, but the drawings represent different moments in time of the same spring. Okay, so we begin with the starting position, and then the red ball goes up, so it's compressing the spring, and then it comes down, goes through the equilibrium point, and at that particular moment it's at its resting length, so it's neither stretched nor compressed. Then it goes down and it's at this point of being stretched, and then it comes back up, goes through the equilibrium point, and then goes back up to being compressed, and then back down to the equilibrium point, and so on, and so on. Okay, so you can see if you follow that graph, keeping in mind that the advance of time is represented on the x-axis, then we can clearly see that we have a sine or cosine wave traced out. Now let's look at this bottom graph just to kind of keep straight in our heads all the different elements of these sine or cosine models. Alright, our y-coordinate simply represents the distance from the equilibrium point, either distance up or down. And then we have our amplitude, which is the amount that it goes up or, that it goes above or below the equilibrium point. That's the amplitude. You could also consider amplitude as half of the wave height. Either way is fine. Either half of the wave height or the distance that it deviates from the equilibrium point. The period is how much time it takes to complete one cycle. How much time it takes for this ball bobbing on a spring to complete one full cycle. That's the period. And frequency is 1 over the period. So if period can be given in units of seconds per cycle, then frequency would be given in units of cycles per second. Now, one quick note before we move on. Remember that when you see graphs of sine or cosine waves, the x-axis actually can have several different units. What we're most used to is the x-axis having units of angle, where you're taking the sine or cosine of that angle, and that results in the difference in y-coordinate. But in this case, the harmonic motion model shows us also that we can use the x-axis to represent time, and we'll end up with the same graph. The x-axis can also represent distance, as it does in physical waves. And physical waves actually have wavelength, not just ocean waves, but even sound waves and light waves have lengths, physical lengths, which are tiny but still exist. Okay, so keeping these drawings in mind, we're going to go on now and see how we can look at the various elements of the sine and cosine models for harmonic motion. Objects that oscillate are said to move harmonically. This motion is modeled with sine or cosine waves that are in this format: y equals a sine omega t, or y equals a cosine omega t. Recall that sine and cosine, really, they're identical curves except for the fact that they're out of phase with each other, that one is shifted with respect to the other. But they have the same basic shape. And we saw that before in section 4.5 when we were talking about tides. Okay, so what are the elements? Y is the distance from the origin, and that coincides with the equilibrium point for these problems, because we're always considering the equilibrium point as the point of rest, and that would be a y-coordinate of 0. So the good news for you is you don't have to worry about vertical shifts. Equilibrium is always going to be 0 here. A is the amplitude. That's just like you're used to. A represents amplitude, the absolute value of A. Period is 2 pi over omega, and actually that's nothing new for you either, because even though they're using a different letter for these kind of models, omega is the same as b, which you already learned. So period equals 2 pi over b, and you can just use a different name for b as they did here, and that's omega. 2 pi over omega, 2 pi over b equals period, and frequency equals 1 over period. Notice also that you have no C term. Remember when we were doing section 4.5 and we did sine and cosine waves, you had A, B, C, and D, and they all represented different things. Well, really, in these kinds of models, you're only dealing with A and B. You don't have to worry about C and D. So they're actually somewhat easier than the models that you did in 4.5. Let's look at this example. A ball bobbing up and down at the end of a spring moves 10 centimeters in either direction from its resting point. The ball travels 10 centimeters per second. Give a sine model for the distance of the ball from its resting point as a function of time. What is the sine model's frequency? Okay, so believe it or not, everything you need to solve the problem is contained in these sentences. You just need to be able to translate it into the different elements of the sine model. Okay, so the one hint I'll give you before I let you do this on your own is that if it's saying the ball travels at 10 centimeters per second, you don't have to worry about acceleration and deceleration and all that. You can just consider that average speed, so don't worry about that. But remember that it's traveling up and down. It's traveling up and down 10 centimeters per second. And if we're considering this a sine wave, that's going to give you a clue about the period. Okay, so pause the video, try to do this on your own, and then resume if you get stuck or when you get your answer. Okay, so as usual with these problems, the key is to sketch correctly. So we have our ball that's bobbing up and down on the spring. We know that the amplitude is 10 centimeters because the problem tells us that it moves 10 centimeters in either direction from its resting point, from the equilibrium point. And how do we know that the period is 4 seconds? Okay, well, if the ball travels at 10 centimeters per second, we know that it covers a certain amount of distance. And so let's look at that distance. If the ball is going from resting point to its uppermost position, so if it's going this way, then it has to travel vertically 10 centimeters. And then it goes back down to resting point. It has to travel vertically another 10 centimeters. And then it goes back down and goes another 10 centimeters. And finally it goes back up another 10 centimeters. And we know that because the amplitude is 10 centimeters. So it has to do that, and it's covering 40 centimeters. But what we do know is that it's traveling 10 centimeters per second. All right, so that means that every trip, either up or down that it goes, takes 1 second. And therefore, if it travels 40 centimeters in one complete cycle, and that's the total distance of how it's traveled up and down, then the period is 4 seconds. If you want to think of it this way, let's think of these as 4 different trips. Follow the mouse arrow and follow. I got 1, 2, 3, 4. 4 different trips. Each of those trips is 10 centimeters. Each of those 10 centimeter chunks takes a second, and 4 times 1 second is 4 seconds. So our period is 4 seconds. Amplitude is 10 centimeters. Now we can figure out omega. Period equals 2 pi over omega equals 4. And solving for omega, we get pi over 2. And so now we can just put it all together and write our sine model for this harmonic motion. And we have y equals a sine omega t, filling things in, y equals 10 sine pi over 2 t. Then the final question is, what is the sine model's frequency? Well, that's easy, right? It's just 1 over the period. And so we have 1/4 cycles per second. Remember that since period is in the units of seconds per cycle, then frequency is the flip of that, the reciprocal of that, so it's cycles per second. And 1 over 4, of course, is 1/4, so we get 1/4 cycles per second. Here's the classwork. We're now at the end of the chapter, so we'll start with review exercises part 1, page 360, 43, 60, 61, page 367, all those numbers. And then we'll go on to review exercises part 2, page 365, all these numbers, and a little note on number 22. For this number, 22, find the speed in miles per hour. All right, so write all these numbers down, and we'll see you in class.